Hello everyone, in this very video we are going to be looking at EMF of a cell, terminal voltage and lost voltage. Now, before we continue, please do well to click the subscribe button below to get notification for our videos. Now we'll move right into the definition of terms. The EMF of a cell is the driving force of current around a circuit. Okay, so the force that drives current around the circuit is called the electromotive force. The EMF, the full meaning is electromotive force. Okay, it is the voltmeter reading when the circuit is open or when no external resistor is connected to it, or when the battery is not supplying any current. Okay, you can use it that way. For terminal voltage is the voltmeter reading when the circuit is closed or when an external resistor is connected to it or when the battery is supplying current. So the voltage when the battery is supplying current is terminal voltage. You can even say it is the voltage across the load. That means the load resistance connected to the battery. So we have the lost voltage. The lost voltage is the potential difference across the internal resistor in the cell. The lost voltage is the potential difference across the internal resistor of the cell. So every cell has an internal resistance. So the voltage, the potential difference across that internal resistance is what we call the load voltage. So we look at the formula, we see a simple circuit here where the EMF, this is the cell having an EMF E, an internal resistance R, connected across a resistor big R. Okay, so we know that the EMF is equal to V plus V. The capital V is the voltage across that's the terminal voltage, which is the voltage across the resistor R. Then our small v there is the voltage across the internal resistor, internal resistance. Okay, so with that we now have that E is equal to IR, according to Ohm's law, V equal to IR. Now, but the small v now is equal to I small r, and so at the end of the day, you can see that the current supplied is going to be E all over R plus R, all over the load resistance plus the internal resistance. The small r represents internal resistance, the big R represents the load resistance, and while E is the EMF of the cell, then I being the current. Okay, so we see a question here. It says a certain battery has a 12 volt EMF and internal resistance of 2 ohms. Find the current, terminal voltage, and the power dissipated by a 5 ohms load connected across it. Okay, let's start by finding the current first of all. We just saw that current in this case is equal to the EMF all over the load resistance plus and the internal resistance. The EMF given is 12 all over the load resistance we are given here is 5 plus the internal resistance here is 2. So that is going to give us 12 over 7 amperes. And we can do well to calculate that. 12 divided by 7, it's going to give us 1.714. So that means our current here is 1.714 amperes. So that's the current in this particular circuit. You can write that somewhere. Okay, so that leads us to the next thing. The next question we have to find is the terminal voltage. Now, since we know our current, we can say that the terminal voltage is equal to I times the load voltage. That's the value for the terminal voltage. Okay, so and that is going to give us the I is the current is 1.714. 1.714 multiplied by the load resistance is 5. Okay, and if we calculate that, we are going to get 8.57 approximately. So 8.57 volts approximately. Now that is it for the terminal voltage. Now the next is that we are asked to calculate the power dissipated by the 5 ohm resistor. Well, we can calculate that in many ways. We can say that the power is equal to I squared R. We can use this since we know the current and we know the resistor. So that is going to be 1.714 squared times the load resistance is 5. Okay, so and that is going to give us approximately 42.86, which is equal to 42.86 watts. Another way you can do that is by saying power is equal to the current times the terminal voltage, or you can say power is equal to the square of the terminal voltage divided by the load resistance. You get the same answer. Now that leads us to another question here. It says, what is the output voltage of a 3-volt lithium cell? That is the EMF. The output voltage there is talking about the terminal voltage. 3-volt lithium cell in a digital wristwatch that draws 0.3 meter amperes. Okay, if the cell internal resistance is 2. Now we have an idea of the EMF, we have an idea of the current drawn. So we can say that I is equal to 0.3 milliamperes, and 0.3 actually, milli there means divide by 1000. So it's going to give us 0.0003 amperes, okay? Or if we like, we can say 3 times 10 to the power minus 4 amperes as our current. Okay, so in this case here, since we are given internal resistance, I can find the lost voltage. The lost voltage here is I times internal resistance small r. So my current is 3 times 10 to the power minus 4 multiplied by the internal resistance here is 2. So we have 2 here. And if we multiply that, we are going to get 6 times 10 to the power minus 4. Or if you like, you say 0.000 then 6. Okay, so that is our lost voltage. Our lost voltage is 0.006 volts. Now, but in this question, we are asked to find the output voltage. The output voltage is also the terminal voltage. Since we know the lost voltage, we can say we can bring back our formula where we have that V is equal to the load voltage or the terminal voltage plus the lost voltage. Now your EMF is 3. We are looking for this, then plus the lost voltage, we just calculated it to be 0.0006. So if we collect like terms, you see that V is equal to 3 minus 0.0006. And when you subtract that, you are going to get 3 minus 0.0006 equal to, you're going to get 2.9994 volts. Okay, so that's the value for our load voltage. We see another question here. It says an EMF 1.5 volts when connected in series with a 1 ohm resistance or resistor. The reading in the voltmeter connected across the cell terminal is 1.40. Okay, determine the internal resistance. That's a very good one. We are given the EMF here to be equal to 1.54 volts, and the cell terminal, the voltmeter connected across the cell terminals is 1.4. That is the reading when connected, the reading of the voltmeter when the EMF or the cell is supplying current. So that is actually the load voltage, or you can call that the terminal voltage, which is 1.40 volts. Okay, so in this case here, we can find the value for the internal resistance. Okay, so how do we find the value for the internal resistance? You can have your E, you can find your E minus V. Okay, which is equal to 1.54 minus 1.40. That is going to give us 0.14 volts. Okay, that we can call that the value of the load voltage, but we don't know what the current is. So how do we find our current? Now we can find our current, so we can write that somewhere, 0.14 volts. Now we can find our current by equating. We already know that the load voltage V is equal to I big R. Okay, so my load voltage from the question is 1.4, and the current, we don't know what the current is, multiplied by R. The capital R here is load, which is 1, 1 ohm resistor. So that means our current here is equal to 1.4 amperes. You can write that somewhere, 1.4 amperes. Now we continue there. with the next thing we are asked, what we are asked to find. So we are asked to find the internal resistance. The lost voltage is equal to the current times the internal resistance. So that means the internal resistance now is going to be the lost voltage all over the current. So which is equal to the lost voltage is 0.14 and the current is 1.4. Okay, and if we divide that, we are going to get 0.01 ohms. Okay, so that gives us the answer to that question. Now we see the circuit here. We are given a circuit and we're asked to find the current in the circuit, okay, and the lost voltage. Now first of all, I want us to see this, that the EMF of this cell is 20 volts from what we see here, and the internal resistance R is equal to 4 ohms. The challenge is with the load resistance is a network of circuits. The two ohms resistor in parallel, and both of them are in series with a 3 ohms resistor. But we can do that. We can find the load resistance to be equal to 2 times 2 over 2 plus 2 for the two that are in parallel, then plus 3 which is in series. Okay, so that is now going to give us 1 plus 3, and that is equal to 4 ohms. So that means the load resistance is 4 ohms. With this we can find our current. Okay, so we can say here that our current I, which is equal to E over R plus R, is the same thing as 20 over 4 plus 4. That will give us 20 over 8. And 20 over 8 is going to give us 2.5. So our current is 2.5 amperes. Now the next is the lost voltage. The lost voltage is equal to current times internal resistance. So that is going to give us 2.5 times internal resistance is 4, and that gives us 10 volts. So that answers that question. Now we see something else here, which is the maximum power in a cell. Now a cell delivers maximum power. Note that when the internal resistance is equal to the load resistance. That means when capital R is equal to small r. And the maximum power is given by the formula E squared, the square of the EMF divided by 4 times the internal resistance. Now just like a question we have here, what is the maximum power of a cell of EMF 10 volts and internal resistance 2 ohms? Remember, at maximum power, the internal resistance is equal to the load resistance. So we can simply say that our P is equal to 10 squared all over 4 times 2, okay? According to this formula here. And that is going to give us 100 divided by 8. And that is going to give us 12.5 watts. So that is it for the maximum power, in a cell. Now that leads us to efficiency of a cell. Now the efficiency of a cell is the power output over power input times 100%, giving rise to R over, that's capital R over capital R plus small letter r times 100, or you can say the load resistance divided by the sum of the load resistance and internal resistance all multiplied by 100. Now let's see how this came about. The power output here, like I say, is the power in the load, so you can call that I squared R. And why the power output here, power input here, is the power, when the cell is not delivering any current, you can call that I squared into R plus small r. Okay, that's very, very key. And this cancels this, and what you are left with is R over R plus R times 100. Okay, now another way we can see this is that the power output can also be IV. That means the current times the terminal voltage divided by the power input is the current times the EMF of the cell. So as I cancels I, remember, times 100, your V here is also equal to IR, and by your E here is I into R plus R. So you see this cancels this, and we are still left with R plus R plus R times 100%. Okay, so now we see a question here. It says calculate the efficiency of a cell with EMF 10 volts. So the EMF of the cell is 10 volts. Okay, internal resistance is 2 ohms and connected in series with a resistor of 10 18 ohms. Now, we are given the EMF of the cell to be 10 volts, but we don't need that to calculate the efficiency of the cell, because our efficiency of a cell is load resistance all over the sum of the load times internal resistance multiplied by 100. So my load resistance is 18 all over, you have here 18 plus 2 times 100, okay? So that gives us 18 over 20 times 100, okay? And the answer here is 90%. Thank you very much. Have a great day. Don't forget to subscribe, and we'll see you in our next class.